Nature has a strange way of adapting to disasters man throws at it. Over the past 150 years, nature has struggled under humanity's most dangerous invention, plastic. 100 million marine animals are massacred by plastic waste each year, and microplastics flood our rivers and lakes, dealing humankind's hand of ceaseless death throughout the entire ecosystem. Imagine the seabed strewn with empty shells from turtles, suffocated by plastic nooses. Imagine whales starving to death with stomachs too full of plastic to digest food anymore. Imagine entire shoals of salmon floating belly up after consuming the tiny bits of broken plastic bags that have washed in from the shore. Imagine all these things and you will not have come close to the scale of destruction that plastic has wreaked on our planet. However, recently, nature has just gifted us with its most bizarre gift yet, leading to a uniquely unusual way of dealing with the persistent threat of plastic pollution. You see, some inventions are made after years of consistent work, and some are made on accident. But what kind of accident prompted scientists to manufacture a biodegradable and infinitely reusable plastic polymer by mixing salmon sperm and vegetable oil? Interestingly, the demand for such a product has been in the market for quite some time. Despite all the talk of the 3 Rs, less than 10% of the 300 million tons of plastic produced per year worldwide is recycled today. To put that into perspective, that's about 800 kilograms of plastic waste produced per year per person living in the US today. And the worst thing about plastic waste? It takes 450 years to biodegrade, which means that by the time all the plastic waste from a single year has been broken down naturally into chemical components that are non-harmful to the environment, an additional 132 billion tons of plastic waste is produced. If you had $1 bill for every 1,000 kilograms of plastic waste produced and stacked them on top of each other, it would be about 38 times longer than the distance between the Earth and the Moon. So scientists have been trying to devise a formula for easily reusable and recyclable plastic for a long time. So, how is this plastic manufactured, and why the strange choice of salmon sperm as a material? This has to do with the certain part of the DNA molecules inside the salmon sperm, the phosphate backbone. You can think of this as the top part of a Lego brick. Phosphorus is what is known as an electrophile, and it reacts with nucleophiles via nucleophilic substitution. What this means is that the phosphorus atom, which likes to receive electrons, reacts with pairs and parts of other molecules that are partially positively charged, which serve as electron donors. Now, we can't connect two Lego bricks together without the bottom half of the brick, which in this case refers to our vegetable oil molecule. So what part of the vegetable oil molecules serve as electron donors? The Chinese scientists actually attached ionic groups to the long carbon chains found in vegetable oil and added those chains to one another via a process called polymerization to make those chains even longer. Now, when the positively charged part of the ionomer, known as the carboxylic salt group, comes into contact with the phosphorus part of the DNA in salmon sperm, they react to form an even longer and even more complex molecule. Now, we have formed one Lego brick, which can react with other Lego bricks around it to form a giant strand of Lego bricks, known as a polymer. However, a Lego brick tower is quite fragile and easy to break in half. In order for this plastic to compete with the stronger alternatives already being marketed, the scientists had to find a way to increase its strength. Luckily for them, the long chains of the vegetable oil molecule and DNA bases were found to interact with each other, making our Lego brick tower more like a piece of chainmail. Now, DNA bases, the colorful rods in the middle of every DNA diagram, are actually hydrophobic, which means that they hate coming into contact with water. It is this powerful interaction between two hydrophobic DNA bases that ensures the DNA strands do not unravel, even in an environment that is 70% water, our body. Hydrophobic interactions operate based on the principle of the enemy of my enemy is my friend, which means that two hydrophobic groups will form a strong bond with each other in order to keep away the water molecules elsewhere. Remember those long chains of carbon atoms in the vegetable oil molecules? Those long chains are also hydrophobes, and therefore they link up with the DNA bases to form a strong and durable mesh. So, the scientists had found a plastic that was as strong as those already in the market. However, most importantly, these plastics were also biodegradable and infinitely reusable. Adding water to these plastics would soften them enough to be molded like clay into any shape they desired. This is because these plastics were also what is known as a hydrogel, a substance that can absorb large amounts of water while remaining chemically unchanged. This water can then be removed from the plastic via freeze-drying them, and they are ready for use in a dry environment. They can also be digested into environmentally and biologically safe molecules via the common DNase enzyme found in every creature with DNA in its body. Some may say that such a plastic serves no purpose because of how it turns soft after contact with water. Yet, we unwittingly use dry plastics that would benefit from that exact property in our daily lives. Perhaps in the future, we would no longer need to worry about the bags for our groceries ending up in the ocean or in the stomach of some poor fish. It would be truly poetic if, in some way, the shoals of salmon saved themselves from an untimely death at the hands of plastic by helping to produce a better plastic themselves.